Hi everyone. As interest in generative AI has surged, so too has demand for Nvidia GPUs, briefly making Nvidia the most valuable company in the world. A large part of Nvidia's success has been due to its Cuda ecosystem, which has long been a massive moat against other companies. However, that advantage is starting to disappear, and Nvidia isn't the only player in the GPU game. Keep watching to learn more. This video has 3 parts: Nvidia's Cuda moat, the competitor's view, and should Nvidia be worried? Part 1. Nvidia's Cuda moat. If you're involved in AI models at all, you probably already know that pretty much all deep learning is occurring on Nvidia GPUs. This includes both training and inference. This fact is the reason why Nvidia's stock price has climbed stratospherically recently and even made Nvidia the most valuable company in the world. As of this video, I think it's the 3rd most valuable company in the world, but still, not bad. Of course, Nvidia makes great GPUs, but their hardware is not the only reason for their dominance. Nvidia has what people call an AI software moat. Basically, Nvidia controls enough of the AI software ecosystem that they can keep competitors out. What exactly is this software stack? Well, let's start with a bit of history about GPUs. Originally, GPUs were only suited for graphics, hence their name, meaning graphics processing unit. GPUs had a fixed function pipeline that was defined in hardware and couldn't be changed by the end user. Eventually, GPUs started to get a little more flexible when shader programming came along. Shader languages like GLSL for OpenCL and HLSL for DirectX allowed portions of the graphics pipeline to be changed programmatically. These languages effectively compiled down to GPU assembly code, which meant that GPUs had to start becoming more general purpose, until GPU companies realized they could actually expose a fully general and fully programmable interface without too much effort. So they introduced GPGPU, or general purpose GPU programming languages. As usually happens in technology, the market leader defined their own proprietary solution, which they kept closed source, while everyone else tried to define an open standard, which never really caught on. The open standard was OpenCL, and the proprietary solution was Cuda by Nvidia. So Nvidia leveraged an initial lead that they had in the gaming GPU market and has built upon and maintained that lead ever since. What made Cuda so powerful? Several important design elements. It's designed to reveal low-level details about how the GPU actually works, in particular the memory hierarchy and also the computation structure. Just like a CPU, a GPU has many different layers of memory arranged in a sort of pyramid, where the smallest is also the fastest. And if you really want to use the entire GPU's memory, that's going to be really slow. But a GPU is particularly sensitive to the way in which you use its memory and its different levels of hierarchy. If you make a mistake, for example, you end up accessing memory in a pattern that's very inefficient, then the performance of your system can really tank. So that's why Cuda explicitly exposes this pyramid of different types of memory so that you can access the right portion for your needs. In terms of computation structure, while CPUs basically just have threads, in Cuda, you work with grids and blocks and threads because GPUs have a much more complicated execution environment. In contrast, the OpenCL standard has been pretty slow to evolve, and OpenCL code is meant to be written once and then run on a GPU or a CPU, which necessarily means hiding many aspects of how the GPU actually works. That also makes it really hard to get the best possible performance out of your hardware when you're using OpenCL. But this may have been inevitable when you get a lot of different companies coming together trying to make compromises and decide on a standard. But I really think they should have kept the CPU and GPU portions very separated. These days, the newer versions of OpenCL, like OpenCL 2.0 and 3.0, are actually optional because they don't have any staying power amongst GPU companies anymore. I think the other part of Cuda's success comes from PTX, which is the machine code that it outputs. Nvidia is not afraid of change, and so the PTX machine code that the Nvidia GPUs support has changed a lot. I think there have been something like 12 or 22 different versions of it so far. This basically means that there are multiple different binary APIs that Cuda can target, which is very similar, by the way, to how the Android SDK works. If you've ever made Android apps, you know that there are like 18, 25, even 30 different versions of the Android API. This is also what ARM assembly code looks like, ARM being the CPU architecture that powers virtually every phone on this planet, including Androids, iPhones, and even Apple laptops these days. Assuming you have a good compiler infrastructure, which Cuda certainly does, I think this is the right model to enable rapid innovation. If Nvidia tried to maintain backwards compatibility with its PTX machine code, that would put a lot of constraints on future generations of GPUs and how they could be optimized. This approach does force people to recompile their code whenever a new version of Cuda comes out, but you can impose that when you are the market leader. Cuda has become so popular that it was very natural for other frameworks to actually target it, meaning other frameworks or other programming languages output Cuda, which then gets compiled by the Cuda compiler into PTX that can actually run. Of course, if something targets Cuda, that means it only works on Nvidia GPUs, because there are two main problems for competitors. First is that Cuda is closed source, and Nvidia really doesn't like anyone trying to copy it. And second, even if you do try to copy it, Cuda has had a lot of features added to it over the years. So it's a really massive task to try to re-implement Cuda. The PTX language keeps changing because Nvidia just has to make a new compiler in that case, but Cuda itself never changes, at least not in a way that breaks backwards compatibility. That's how Nvidia makes sure that its customers don't have to keep changing their code for new generations. And Cuda has had such a huge market share, and it's so complicated that if there are any bugs or quirks in the implementation, then that's actually what people rely on, which makes it even harder for someone to replicate, because they would literally have to replicate all of the bugs as well. Just as an example, Pytorch, the most popular machine learning framework out there, used to target Cuda exclusively. So even though Nvidia doesn't control Pytorch, which was originally created by Meta, they effectively guaranteed vendor lock-in for Pytorch, and therefore for everyone that uses Pytorch, which means the entire machine learning community, basically, outside of Google, which creates a huge amount of momentum that's really hard for any competitor to imagine changing. And there's also just the simple fact of human nature, where if your previous cluster was built entirely of Nvidia GPUs, your next cluster probably will be as well. Part 2. The competitor's view. Let's take the perspective of an Nvidia competitor for the moment. It's really hard to break into the GPU market, especially the machine learning part. Nvidia has been involved in arguably anti-competitive practices to make sure they control the software stack. So if you're AMD or Intel or some other producer of hardware accelerators, how would you approach this issue? Actually, nobody likes the Cuda monopoly except for Nvidia. Even Pytorch, which I mentioned, wouldn't have restricted itself to Cuda unless there was no other good alternative out there. Companies like to have additional options beyond just the primary provider. For example, Google wanted to build Stadia, their online gaming platform that eventually flopped. But anyway, when they were building it, they decided to use entirely AMD GPUs. And it makes perfect sense. Google would get better performance per dollar and a partner that was presumably more willing than Nvidia to share details of how their drivers were really working. Companies also just hate relying on a single company because they see it as a single point of failure, right? If that company messes up or can't meet production targets or whatever, then you have nowhere else to turn to. So there's definitely a market for Nvidia competitors, even if the hardware isn't as good, if you can just break this Cuda nut. So we're going to talk about 4 different ways that companies could address this issue. First, companies could try to have hardware compatibility. It's definitely the simplest way to approach this problem. For example, AMD CPUs are hardware compatible with Intel processors, which means that AMD doesn't have to have a completely isolated market for its CPUs, because a program compiled for an Intel CPU can just run on an AMD CPU, in theory. This was only possible because Intel had a sort of open standard. They published the details of how their architecture worked. And this can backfire on you. For example, AMD was the first to produce 64-bit Intel-compatible processors. So in many cases, it actually got their name. Although the official name of 64-bit Intel processors is x86_64, Debian Linux still refers to this architecture as AMD 64. And anyway, this worked because Intel has a very stable architecture. They actually implement their machine instructions by having some microcode underneath, and the microcode can change all the time, but the instructions do not. In theory, you can run an original 8-bit program designed for the 8080 on today's 64-bit processors. It's actually a little more complicated than that, but still, it's the thought that counts. That meant that AMD could target the same stable architecture. But as I mentioned, PTX is very unstable. So maintaining hardware compatibility with Nvidia would be next to impossible. You'd have to try to target the stable API, which is basically Cuda in this case. The second way to try to maintain compatibility would be to have library compatibility. Just take all those Cuda functions and rewrite them and have your own version. While this is definitely feasible, it doesn't solve the issue that you have all this user-written Cuda code out there, and it's also very difficult to do when the API is really large, which Cuda is. Like I said, they just keep adding to it. So for example, when IBM tried to take their database, DB2, and make it compatible with Oracle, they were able to do so because it was a relatively small API difference, and then they were able to slurp in all of Oracle's customers. When Microsoft tried to port Linux to run on Windows, they were successful. That's what's now called WSL, Windows Subsystem for Linux. And that's because Linux has a relatively small number of system calls, about 300 or so, that have to be implemented for that to happen. But the other way around, when the Wine project tried to get Windows to run on Linux, is essentially hopeless because there are more than 2,000 system calls in the Windows kernel. And it's also not a stable API, which is why Wine stands for Wine is not the best. Oh, wait a minute. I think I got that one wrong. Wine is not an emulator. That's right. It's a library compatibility layer. Third option is to do binary translation. If you have a program written for one processor architecture and you want to run it on a different processor architecture, then you can technically translate every instruction so that it works properly on the new architecture. This is very hard technically and a lot of maintenance effort, especially, as I mentioned, because PTX is not a stable API. There are some pretty successful examples of binary translators out there though. For example, when Apple started using ARM processors, or Apple Silicon, in all of its laptops, they were faced with the issue that all the Mac programs out there were compiled for Intel-compatible processors rather than ARM processors. Now, Apple isn't as afraid of breaking backwards compatibility as Windows and Intel are, but they still had to do something about this, or the brand new laptops wouldn't be able to run any programs. So they created Rosetta, which is a complete binary translation framework between x86 code, or Intel code, and ARM code. And although there are definitely edge cases, a large number of programs just work out of the box, which is simply amazing given the technical details of what it's actually accomplishing. Finally, the fourth and probably most difficult route you could take to try to achieve compatibility is to create an entirely new compiler. This is also a difficult task because you have to implement all of the Cuda libraries and also pretty much match all of its quirks and keep up with all the new updates that Nvidia keeps adding to the language. And writing another compiler is a really easy way to get into legal trouble. If the compiler that you're copying belongs to a company that's likely to sue you, which Nvidia certainly is in this instance, then you have to do what's called a complete clean room reimplementation, which means that you go and create a compiler without ever referring to any code that could possibly be copyrighted by the other company, which means no looking at their compiler to see how it works, no running it, you just have to work entirely off of documentation from their website, for instance. There's one really famous instance of a company doing a clean room reimplementation of a compiler. Google was out looking for a language that it could use for its upcoming Android smartphones, and it thought that Java would be the perfect fit. But Oracle owned all the rights to the Java compiler, and they didn't want to let Google use it. So Google did a complete clean room reimplementation. It took a long time, and unfortunately, Google's compiler was open source, and someone, I think from Oracle, ended up looking at that source code and saying, I think this tiny function right here looks like it was copied from our code. So Oracle sued Google over it, and I think Google lost that case and ended up paying a fair amount of money to Oracle for what was really a short function, just a few lines long. But because there was reasonable doubt as to whether that function had actually been recreated or was really copied from the internet from Oracle's code somewhere, it got them into a lot of trouble. You can also do a lightweight version of this, which is basically source-to-source translation. So you can have a tool that takes Cuda's source code as input and outputs source code in another language that works with your hardware. And currently, both AMD and Intel have this sort of tool in their frameworks. Now let's talk about how some of the direct competitors to Nvidia, namely hardware manufacturers, are going about using these 4 different techniques to try to make their systems compatible with Cuda. First is Intel, which, since they started producing ARC devices, are now manufacturing dedicated GPUs of their own. Intel's equivalent to Cuda is called OpenAI. And as mentioned, they have some ability to translate Cuda programs into OpenAI code. There was also an Intel engineer who created this system called ZLuca all in his own time, which was meant to be a reimplementation of Cuda that would run on Intel GPUs. The project was shut down for a while as Intel decided to evaluate the business case for this software, and they eventually said, nah, just release it open source. We don't really want to pursue this direction. So this developer went to AMD, who's the other major producer of GPUs these days, and worked with AMD to start porting it to their GPUs. And then AMD came along and said, let us evaluate the business use case for this. And then eventually they also turned down the opportunity to have a complete reimplementation of Cuda. Basically, both of these companies realize that they could get into a lot of legal trouble if Nvidia decided to press them on it, which they almost certainly would. But AMD and Intel aren't the only GPU producers in the world. Although you may not have heard of them, there's a company called More Threads, which I think is a great name. This is a Chinese company that was founded in 2020 and then released their first GPU products in 2022. Apparently, these GPUs are not very fast at all, but if you're in China, remember that the US government has banned Nvidia from selling their highest performing GPUs to China. So the bar is lower for More Threads. They only have to compete against pretty slow Nvidia GPUs. So if More Threads can get the costs down, then they'll probably start to look appealing. Anyway, the company has this tool called Musify, which is designed to allow CUDA code to work with its GPU architecture, which they call Musa. The English internet is pretty light on details about this system, but according to an architecture diagram I found of the More Threads product, they seem to be re-implementing most CUDA components. And Musify seems to either be a full compiler of CUDA source code or possibly a binary translation framework. My guess is they're trying to do both. They can probably compile unmodified CUDA code without too much difficulty if they've already re-implemented all of the CUDA-style libraries. But to a Chinese consumer, having a binary translation tool is probably ideal because you can't necessarily contact the provider of your software and say, hey, can you please compile for a More Threads GPU when they may not have heard of More Threads. The other reason I think that they're doing binary translation is because of NVIDIA's response. NVIDIA banned the disassembly of code that is linked with Cuda. Let me unpack that. So typically, disassembling code to understand what the instructions are doing at the assembly level is always possible in a technical sense, but it's often banned from a legal sense because companies don't want their closed source proprietary software from being unraveled and replicated. Of course, if you're located in China, you probably don't pay much attention to these sorts of bans and are pretty happy disassembling a competitor's code anyways. But NVIDIA went a step further. Instead of banning the disassembly of their own code, like the Cuda libraries, for example, which would make sense and would have precedent, at least in a Western legal setting, they literally banned you from disassembling your own code after you've compiled it if you're linking it with the Cuda libraries, which is bizarre. I'm not sure it would hold up legally speaking, but they probably did it because they don't want people running binary translation tools. For example, something like Musify, which a company could use to make their product compatible with More Threads GPUs. Of course, it doesn't help very much against someone in China, for example, More Threads themselves, from running the disassembly of your code and therefore translating the software for you. Because whatever NVIDIA says is pretty unenforceable in China. So I think this is more of a gesture than anything else to let the market know that they're really serious about protecting the intellectual property, which is Cuda. And after all, as one commentator put it, recompiling existing Cuda programs remains perfectly legal. So if More Threads, or anyone else for that matter, manages to actually implement a clean room version of a Cuda compiler, there's not much that NVIDIA can really do about it. So let's talk about new compilers. Amazingly, there's actually a company called Spectral Compute based in the UK, which came out with an entire clean room reimplementation of a Cuda compiler. Their compiler is called Scale. It currently targets AMD GPUs, although they're planning to support even more types of GPUs in the future, which I guess means probably Intel GPUs and not More Threads GPUs. Even more amazing is that this compiler is currently free. It's unclear whether it will stay free because they're calling it a beta right now. And it's closed source, not open source. But that's only sensible when you're doing a clean room compiler reimplementation. You don't want to have to prove that this one little tiny function here was not copied from the internet. Also, this compiler took 7 years for them to build. That's right, it took 7 years to create a clean room reimplementation of a Cuda compiler. Now, Spectral Compute is a fairly small company. They have less than 50 employees, according to LinkedIn, and they do other things, but still, it just takes a huge amount of effort to clone something as vast as Cuda. I don't know what their intentions are, but if I were them, I would be trying to drum up interest and support for using this software, get a lot of people interested in it, get AMD really interested in it, and then start charging people for using the compiler, and get Nvidia to buy you out so they can make the compiler free again so that everyone keeps using their GPUs. Anyway, AMD has basically been doing that already through a different path. AMD has this compiler called ROCm, which is basically their answer to Cuda. It's supposed to support a lot of the same use cases, but it has been very spotty in the past. Basically, AMD didn't set out to try to create a general purpose computing engine the way that Nvidia did. Instead, they just added features to ROCm that were needed by their biggest clients. So hobbyists and machine learning developers that tried to use it found gaping holes. Of course, their attitude towards machine learning has recently changed rapidly. So in October 2023, AMD acquired Nod.AI. Nod.AI had their own optimizing compiler, which already targeted AMD GPUs. So it wasn't exactly Cuda in a box, but it brought AMD much closer to actually having a working Cuda compiler. I think they've now merged all of that into ROCm and continued development there. It seems like AMD is continuing to put a lot of resources behind this project. As part of the research for this video, I actually spoke with an AMD compiler engineer who was working on all of this stuff. I didn't get any details, no NDAs were broken, but he did say that all of the work that they're doing is open source. And indeed, most of ROCm is open source. It's a typical strategy when you're behind, as I always say, open source when you're behind to try to leverage the community to catch up to your competitors. But it's a really sound plan by AMD. And if it doesn't work out, they can always buy scale. Part 3. Should Nvidia be worried? First of all, this section and indeed this entire video is not financial advice. Please don't invest or not invest based on what you see here. On the one hand, all of these techniques that we talked about that other companies are trying to do are fundamentally catch-up techniques. They're ways that other companies can try to copy the market leader, which is clearly Nvidia, and really try to breach the software moat that Nvidia has built for itself. Remember that Nvidia still makes the best GPUs. On the other hand, AMD already provides, arguably, better performance per dollar spent, especially on the lower end. So Nvidia would probably experience significant downward pressure on their prices if their competitors were playing on a level playing field. So even though it's not an existential risk to Nvidia, they still want to maintain their CUDA monopoly as long as they possibly can. And also, of course, their sky-high valuation. My perspective, though, is actually that CUDA is just too large and complicated to be effectively emulated. Nvidia just keeps on adding to the framework. If you're Scale or ROCm, then you're constantly going to be on the back foot, constantly a generation or half a generation behind. Nvidia is also very wealthy now and can enforce its moat in many different ways. If it comes to a bidding war, Nvidia can easily outbid AMD when it comes to purchasing Scale, for example. However, all that said and done, even Cuda is not actually the most ideal framework for general purpose GPU programming. Why? Well, the same reasons that make it really hard to copy. It's super complicated, which means that a simpler language and a simpler framework might actually perform better. Similar to how ARM processors can outcompete x86 processors when it comes to power consumption and all kinds of other metrics, because x86 processors are carrying around 3 or 4 decades of baggage. So there's actually one extra dimension that we haven't talked about yet, which Nvidia should be most worried about. And that is, what if a competitor introduces a more attractive stack? Now, this would be very hard to do. The competitor would need to have a significant advantage in at least one area for their hardware. Otherwise, you would just keep using the Nvidia hardware and the Nvidia stack that you're familiar with. It's also, as you can guess, extremely capital intensive to recreate an entire stack like this, and it takes quite a lot of time. So any company trying to do it would have to take capital from some other line of business that they're already successful in. AMD could afford this though, because they have pretty successful CPUs. And interestingly, we can actually get a good idea of whether and when this is happening, because again, when a competitor is playing catch up from behind, they will often release their products open source to try to leverage some community involvement for that extra little bit of effort. And as it turns out, new stacks are actually being quietly created all the time. Most are really special purpose, but not all of them. This information is from an article by Semi-Analysis, which you can check out in the links below. Basically, they highlight OpenAI's Triton and also Pytorch 2.0. Pytorch, remember I said, has historically only supported Cuda as its backend. And part of that was because there was just layer upon layer of different operators and different features added to Pytorch until they had this huge API that they had to maintain. But they went back and rewrote a lot of the graph planning aspects of Pytorch. They called that Pytorch 2.0, and as it happens, it's much more compatible with the way that other GPUs want to do things. So suddenly Pytorch, which is this aspect of the stack that Nvidia doesn't control, is making itself more compatible with other GPUs, which is not something that Nvidia wants. But the really interesting development here is OpenAI's Triton. Basically, OpenAI has a lot of machine learning experts, but not very many GPU programming experts, or so I gathered. So they created Triton, which is a domain-specific language that's implemented on top of Python. As is very common for these sorts of languages, you just write Python functions and you add a little annotation at the front, which basically says, Triton, pay attention to this. This means that the same people that are writing Pytorch every day and are therefore very familiar with Python can actually try their hand at writing Triton code, which is certainly not the case when it comes to Cuda. Cuda is extremely complicated code to write, and you really need to think about it a lot, and you need specialized skills for it. Triton is a higher level version of Cuda that nevertheless achieves pretty similar performance. And Triton does this by turning its code, that Python-based stuff that the programmer wrote, into an intermediate representation that's compatible with the LLVM compiler framework. I'll talk about that more in a minute, but it's basically something that exists inside a compiler, and then they use the existing LLVM support for outputting PTX code. If you remember, PTX is the name of the assembly language, or the GPU machine language for Nvidia's GPUs. In other words, Triton is skipping Cuda completely. They don't go from Triton code to Cuda to PTX and then run that. Instead, you just go from Triton code straight to PTX and then run it. This is really dangerous for Nvidia because it cuts Cuda out of the equation and makes it much easier to port to other architectures. Let me stop and explain a bit more about LLVM so it will make more sense. If you're not familiar with LLVM, it's basically a research compiler that has slowly revolutionized every aspect of compiler technology. It's the first system with an intermediate representation for the code that's flexible enough to handle high-level information and low-level information. It's now used in the V8 engine to accelerate JavaScript in your web browser. It's used for traditional C and C++ compilers. It's used for new compilers like the Swift programming language that came out of Apple. Heck, even the Linux kernel that runs in Google and Meta data centers is compiled with LLVM. And basically, every researcher who's doing any kind of optimization research is going to make sure that their code works with LLVM. So there's a faster improvement loop for LLVM-based techniques. Improvements to LLVM code generation can immediately propagate to all these other uses of the technology. And because there's only one intermediate representation, it's really easy to write new source languages or new output languages. For example, new versions of PTX, or supporting AMD GPUs as well, or supporting Intel GPUs as well, etc. So as Nvidia, unless you develop your own LLVM-based system, you're probably going to lose in the long run. But unfortunately, having an LLVM-based system means that you can't really have your own proprietary compiler and proprietary framework anymore. It's much harder to add value there. So the existence of LLVM actually really shrinks this moat, and the fact that people are already using it and targeting PTX shrinks the moat even more. On the other hand, though, all of these companies that are investing in these types of technologies have to pick and choose where to put their investments. For example, even Triton only supports the things that OpenAI needs it to. For example, they only support Linux. But that would be a very good match for most clusters out there, which I think run some variation of Linux. And as I mentioned, Cuda still has a lot of momentum as well. For example, Triton was first released 3 years ago, and Nvidia is still doing fine. However, support for AMD GPUs, specifically support for outputting ROCm 5.3, was only added to Triton on July 12th of this year. Before that, OpenAI had no use for it because they had only Nvidia GPUs, presumably. So I find it very interesting as well that OpenAI, presumably, has decided to start adding support for AMD GPUs. Maybe they're considering an alternative supplier. Or maybe Sam Altman just wants to make sure that when he finally gets his own chip company up and running, that OpenAI will be able to use their GPUs with minimum possible friction. So yes, Nvidia should definitely be worried. Their moat seems to be getting eroded by new technologies like LLVM, seems to be getting eroded by new projects like Triton, and also projects like Pytorch that used to be exclusively Cuda focused, now sort of spreading out and supporting, in theory, other architectures. Besides Cuda itself being under attack by this clean room compiler, and also AMD potentially improving ROCm to the level where it can actually run Cuda stuff a lot better. Nvidia certainly has tons of momentum on their side, and months or years of pre-orders to pad their bank account. But if you've looked at this topic on Reddit recently, you'll see a lot of people saying that with Pytorch 2, they could basically get their AMD GPU up and running. They still expect lots of little issues. After all, deep learning has run on essentially the same stack since its inception, or at least since Pytorch was invented. So common wisdom in the machine learning community says that Nvidia is the only feasible way. Even I bought an Nvidia GPU for machine learning, so you can imagine what a corporation would do. They would just follow the common wisdom. Unless, of course, there is the potential for them to save a lot of money with just a few technical road bumps along the way. Surely those can be easily sorted out, right? Someone has to be the first, after all, to build a billion-dollar AMD cluster. Finally, in conclusion, we talked about the moat that Nvidia has built to protect itself from competitors, and why the software portion of their stack, Cuda, is such a big component of that moat. Cuda reveals the low-level details that let programmers extract maximum possible performance out of their hardware. And because Nvidia GPUs were the best, everybody just targeted Cuda, and that became a self-fulfilling prophecy. On the other side, though, there are lots of companies, pretty much every other company, in fact, that would really like to break this monopoly. We identified 4 different ways that a company could try to do this. The first 3 ways actually have potential legal difficulties, and they are hardware compatibility, library compatibility, or binary translation. The third way of creating a new compiler to recompile all the code is also very difficult, but there's at least one company that has succeeded in that. Spectral Compute has made a clean room compiler that they call Scale. There are also projects like OpenAI's Triton that actually bypass Cuda completely by using newer compiler technology to do the heavy lifting for them. Using the LLVM compiler framework, you can bypass Cuda completely, still get optimization, and output Nvidia machine code directly. And presumably, not that hard to add support for AMD or Intel GPU machine code as well. Because Nvidia has so much momentum behind it, I wouldn't really worry about them in the short run. But in the medium run, seems likely to me that there will start to be a lot more competitors, and then there will be downwards pressure on the price that Nvidia can charge for their GPUs, and that will make Nvidia stock do really poorly, and that could be a bit of a negative cycle for them. Big companies have lots of incentive to find a different approach than just paying whatever Nvidia asks. And to be clear, they're charging really high margins for their products. They have about a 75% gross profit margin right now. So that's a long way for their prices to fall. Please like and subscribe, and join our Discord channel if you'd like to talk to the community and to me directly. If you liked this video, check out this previous one I made where I talk about how GPUs actually evolved. It's pretty technical, but it's similar to the one you just watched, so I hope you like it. Well, that's all I have for today. Thank you very much for watching. Bye.